nanohub.org.
Online simulation and more for nanotechnology.
Why don't we go ahead and get started? It's a real great pleasure to have Dick Ehrenkiel with us today. Dick is one of the leading experts in this field of characterizing recombination processes in semiconductors and photovoltaic materials. So it's a real treat to have him come and share his wisdom with us. Dick is a research professor now at the University of Colorado Boulder. Mm-hmm. He's also a fellow emeritus at National Renewable Energy Lab and a consultant there. I found out his first job was at Eastman Kodak, right, where you did some of the first work on electronic photography.
We did. We did, yeah.
And then you moved to Los Alamos, where you worked on laser fusion.
Right.
And then I think you moved to NREL. It was probably called CIRI then.
It was called CIRI, yeah.
And you got in this field of materials characterization. And that's when I first became aware of you. In the early 1990s, we started collaborating. I was looking at my CV last night to refresh my memory.
Yeah.
Between about 90 and 95, we wrote 18 papers together. Remember that?
I didn't know. I know there were a lot. Yeah.
It was kind of fun to read the titles and remember that. Remember that experiment where we etched the substrate off a gallium arsenide thin film and increased its lifetime from 1 nanosecond to 1 microsecond?
That was one of the best ones, yeah.
We had all kinds of fun.
Right.
And now the last time Dick was here was about 91 or so.
Probably.
We were working on a book together.
Yeah.
We kind of lost touch with each other.
Yeah.
So it's a real treat to get him back here at Purdue for a couple of days. So I guess you're a bit of a Midwesterner. I don't know if you grew up you did your...
Springfield, Illinois.
Central Illinois.
Right, yeah.
It is BS, MS, and PhD in physics at Illinois.
Right.
So returning to the Midwest. So would you please join me in welcoming Dick Ehrenkiel.
Well, thank you, Mark. I appreciate the kind introduction. I guess one way you might look at this is I've been a migrant worker, but the other way is I have been around, had a chance to work in lots of different technologies, and one of the most pleasurable times of this whole adventure has been working with the Purdue group and Mark and others here and the exceptional graduate students that came out of Purdue. So that's been one of the real pleasures, certainly one of the high points. I went from Los Alamos to CIRI, as it was called back then, and it turned into NREL in the early 90s. And when I came into CIRI, it was kind of an open position in the characterization group. They really weren't sure what they wanted me to do, but I found very quickly that all of the researchers wanted to measure something called lifetime, carrier lifetime. And I really didn't know anything about carrier lifetime. I'd taken the course like you all have and remember there was something called carrier lifetime. So we started looking into how do you measure carrier lifetime. Well, there were a lot of exotic materials, and there was still a residual amount of silicon going on. Well, at that point in time, the way people measured carrier lifetime, this is the lifetime the electron-hole pairs have prior to recombination, the 1/E lifetime. And the way they did it back then is they painted 4 contacts on a silicon wafer, connected one side to a battery and the other side to a oscilloscope, kind of a 4-point probe, and they had a flash lamp, and they watched the carriers decay via photoconductive decay, and then they threw the wafer away because it was forever contaminated. So one of the first emerging materials at that time was gallium arsenide. Gallium arsenide was a subject of quite a bit of research, and nobody knew how to measure gallium arsenide. I had a talented technician named Donald Dunleavy that I brought from Los Alamos. He'd been in the chemistry and physics department at Kansas City before coming to Los Alamos, and he started talking about, well, the chemists do this thing called time-resolved photoluminescence. So we set up we inherited a bunch of lasers. I came in right at the end of the Carter administration, and we had an abundance of equipment had been bought, but nobody knew how to run it. So I think the main reason they hired me is maybe you know how to run this stuff. We have this whole room full of equipment up here, and nobody knows how to run it. Well, we had pulse lasers, and so we set up this experiment with pulse lasers and started doing something called time-resolved photoluminescence, and we could measure carrier lifetime and things like gallium arsenide. And that's how I got started in this area, and I've been stuck with it ever since. I should mention my collaborators on this work. Steve Johnson was my graduate student. He was so talented I managed to talk him into coming to NREL. And Darius Kousiakis, I think just came there recently to help with the time-resolved photoluminescence. So these two are really running the lifetime business at NREL right now. I'm going to talk about techniques that are available. Now I mentioned painting contacts on silicon with silver paste, and of course that's passé. Everything now is contactless. Time-resolved photoluminescence is certainly one of the top techniques out there, and it's very, very useful, and you are doing it here now. Probably the other mainline technique is something called transient photoconductivity by microwave reflection, and I'll talk a bit about that. This is commercially available. This is commercially available now. We built one of the first ones at NREL, but now you can buy it, as you guys have recently done. Then there's something, the quasi-steady-state photoconductivity, QSSPC, that was developed by Ron Sinton out of Stanford. I bought one of the first ones that came out. This is only useful for wafer silicon. It's not applicable to any other material. It's really the same kind of thing you do with contacts, except rather than painting contacts, he has a coil. I think they run about 10 megahertz pickup, and they flash a long duration, like milliseconds long, and they look at the photoconductivity, and then they use algorithms to extract carrier lifetime out of that. This is the mainstay of the silicon wafer industry, I would say. It's quite cheap, and everybody quotes QSSPC. The downside, not only does it only measures silicon, but the algorithms sometimes don't give you the right numbers when you measure things this way. Sometimes the lifetime deduced by the built-in algorithm is about right, other times it isn't. So there's some problems with it, but it is a very useful technique. We started looking at other ways to measure, well, I guess what motivated this was the thermal photovoltaics program, small band gap materials that were a mainline program of NREL at the time, led by Mark Wanless, and these all had IR band gaps, so we didn't have any detectors for TRPL to work. So I think this was one of the motivations for developing another photoconductive decay technique, and I did a patent on this in '99, and we did a couple others. This is something Don Dunleavy and I, it was really his idea, developed it out of School of Mines a few years ago, and we just had a patent granted on that. And this is more of a laboratory technique. I don't think it's really going to be all that generally viable, but it does enable us to extract some information we can't get any other way about photoconductive decay, and this is the transient free carrier absorption. So these are commercially available. These aren't. I started my own company here about a year ago, which basically incorporates these two techniques right here, and also microwave reflection. And I do contract work for companies and so forth. And I still have a strong collaboration in a little lab space at NREL where we're doing R&D down there. So, the measurement physics, TRPL, time-resolved PL, measures the rate at which photons are emitted from excess carriers excited by a pulse light. So you have a pulse of light, you get a bunch of photons coming out. It works great for direct bandgap materials. It does not work well for silicon because it's indirect, and the pulse, the light photons are just too not abundant enough to measure. APCD measures the excess photoconductivity. Again, you have a pulse light source, and you measure the transient conductivity, which is a product of delta N, delta mu, or delta N mu, whereas this measures delta N directly. So one of the advantages right away of TRPL is you don't have to worry about this. And it turns out this is a concern because the mobility does depend on injection level, and it changes with time. So this can distort the decay curve away from the true lifetime. Other complications, the lifetime of all these lime. I think I did this during happy hour. Lifetime is dependent on injection level and all the above processes, both in the radiative recombination and in the dominant recombination that controls silicon, which is defect, or Shockley-Reed-Hall recombination. And I haven't put a lot into that right now, but basically high-grade direct bandgap materials like gallium arsenide are limited by the intrinsic band-to-band. This is one of the subjects of our book in 1992. So it only depends on the excess carrier density. The lifetime in things like silicon are related to deep level defects. They're called Shockley-Reed-Hall defects, where there's a sequential capture of a minority carrier, then a majority carrier. And so it's a defect mitigated lifetime, whereas this is inherently intrinsic unless the material is not good, and then the defects come into play too. So lifetimes are dependent on injection level. And then we have some artifacts to deal with, like we had in our discussions this morning. We have surface recombination velocity, and we have shallow traps, which distort these decay curves away from the true lifetime and make our life difficult, because we have to extract the real recombination lifetime from these artifacts. Now, the surface sorry about this. The surface recombination velocity we get rid of in the device because we'll have some passivation layer on it. But the shallow trap's a little bit tougher to find our way around and find out how much is contributing. What a shallow trap is, it's a defect that will capture the minority carrier, but it will not serve as a recombination site. So the minority carrier will be captured, it'll sit there, and it'll be thermally emitted. And so there have been some real contentious issues about whether a lifetime from a particular researcher was trap related or whether it was intrinsic. We would like the lifetime to be intrinsic because that will predict how the material is going to work, how good a solar cell will be. If you can get an artificially long decay time from traps, which really do not represent the material. And so that has presented some issues in time when a contractor thinks he had a good material and the project manager thinks it's not a good material, and what's the real answer? Well, this is the basic time resolved PL, single photon counting, which we adopted in the middle 80s. You have you have a pulse laser. Here's a sample. A bunch of electron hole pairs are generated. Photons come out. You collect the collection optics. And you focus the light on a monochromator to the band edge, the band-to-band radiation, and now one is able to see single photon events. If we connect a fast oscilloscope here, we'll see these little photon blips actually coming through the electronics. Now, the way the system works here is the photon emission rate is much smaller than the repetition rate of the laser. So typically every 1,000 events or so we'll pick up one photon. It'll get amplified and it'll come out here and it'll start the stopwatch, which we call the time amplitude converter. This is really a ramp, and so a voltage ramp starts as soon as it gets a photon, as soon as the laser goes off, and it stops when a photon gets there, and the height of the ramp is an indicator of the delay time. That delay time goes in a bin, so every photon we collect, we catalog, we put in a bin, bin, and then as time builds up, we build a histogram of the decay events. So out of that, we are able to get the lifetime of the material. This is something recently from Anrel Metzger, 2008, on SIGs, TRPL of SIGs. And I show this because SIGs has an amazingly long lifetime for a polycrystalline material. This is a very popular thin film material, and it's 100 nanoseconds or more, whereas most thin film materials are in the nanosecond range. These data show that the CAD sulfide component of SIGs preserve this lifetime. If you take it right out of the furnace, you get the dotted line. If you put CAD sulfide on it, you have the green line preserved for perpetuity. If you don't treat it, it decays in a day or two and you lose the lifetime. So this showed that the primary function of the CAD sulfide in SIG cells is to passivate the surface. But anyways, it's also a fine example of TRPL. So here we're counting photon counts, and here's time. Very simple. So each photon that came out, got collected, got put in a bin. This was in the 30 nanosecond bin, for example, and then you build up this histogram. Okay, this is the apparatus that I put together in the late 90s, and it's what I call resonant coupled photoconductive decay. Again, you have a pulse light source. The sample sits up here on an insulating platform. We have had a number of configurations, coils, dipoles, and so forth. We have an antenna here that's connected to this circuit, this resonance circuit. This is a very high Q circuit, which all you electrical engineers know what I'm talking about. Quality factors, we aim for one of about 40, and the reason being there's this trade-off between sensitivity, which increases with Q, and time response, which decreases with Q. So the antenna is hooked to this very high Q circuit. We mixed the, we have an oscillator, which we drive this around 430 megahertz, which is this resonance frequency, and it depends on each one that's made. We'll have a different resonance frequency. And then we got have some little tuners built in and so forth, so we can tweak this up. And then we do a standard audio kind of thing or radio kind of thing. We mix it with the driving frequency and take the sum and difference, and the difference is the DC, and that gets displayed on the CRT. So we convert the RF amplitude to a DC amplitude, and we get a transient, and that gives us our lifetime. Here's a analysis of the system I had at NREL. I now have at my company, but this is...
Excuse me. Could you explain a little bit the physical principle of how that works?
Okay.
Maybe you'll explain a little bit later.
The prior apparatus. Okay. Oh, okay.
Picking it up.
Yeah. Okay, I'm sorry. Let me do this. So the sample is coupled to the resonance system here. It changes the resonant frequency depending on its conductivity. I'm glad you brought that up because that's quite important. So without a sample there, we would get a very steep curve peaking at some frequency. Now we bring the sample, and the sample, it becomes a component in this LCR circuit, and it becomes a conductive component, and the conductivity lowers the Q and lowers the frequency. So the conductivity of the sample changes the characteristic, which I'll now show here. Without the sample there, we would get a sharp spike here, somewhere around 430 or something like that. But when the sample is brought into position, it couples to this tuned circuit, changes the resonant frequency and the Q, and we change the coupling via the spacer so that we get a Q in the neighborhood of 40 or so, which is what we have here. So the sample has done this, and here's a sample in the dark. This is float cone silicon. So when the sample is in the position that we decided on, we like the impedance frequency curve looks like this. Now I turn on a microscope illuminator. It changes the conductivity of the sample. So the LF curve changes to here, and a little more light changes to here. So this is basically the principal operation. As we increase the conductivity of the sample via light, we shift the resonant frequency to the lower frequency the resonant frequency to the lower frequency. If we monitor one wavelength, say 430 megahertz, and we put on light, we see that the impedance of the entire system changes. And that's the basis of this resonant coupling idea. Now, the higher the Q, the sharper the slope, the more it would change. But the penalty for doing that, for increasing the Q, is the response time varies as 1 over Q. So with the Qs I have here of 30 or 40, the response time is 20 or 30 nanoseconds. Now I could have a Q of 1,000, but the response time would be a millisecond. So it's a trade-off between sensitivity and response time. So it's basically coupling the conductivity of the sample, which is increasing with light bias, and that causes a change in the impedance of the entire circuit. So it's really like FM modulation in effect. We change the resonant frequency with conductivity sample. So in a transient measurement, what we do is we sit at one particular frequency, and then the light pulse comes on, and then the excess carriers are generated, and then the decay. Yes, sir?
Why the change in conductivity changes the resonance frequency? Because resonance frequency is 1 upon square root LC.
Right. If you look at the classic LCR circuit, say parallel resonance circuit, the resonant frequency is something 1 over LC. Resonant frequency squared is 1 over LC minus 4R squared over 2L, something like that. In other words, the more dissipation, the lower the frequency. So the higher the conductivity, the lower the resistance, the lower the frequency. So it's basically just that simple circuit. I had that in a slide, but I don't think I included it today. So it's basically just changing the resonant frequency of that circuit by its coupling with the sample. So, okay. So in practice, here's a float zone silicon wafer, which is passivated. No, it's not passivated. In air, put it on the platform. We measure 18 microseconds. Now, the group at MIT some years ago discovered this magic that if you take a silicon wafer and drop it in an iodide methanol solution, it passivates the surface states. These are the dangling bond states due to the termination of the surface, which is the bugaboo of all electronics. So we drop it in iodide methanol after cleaning it a bit, and you see the real lifetime is 666 microseconds because the surface has gone away. Surface has been passivated. And so this enables us, basically we put the wafer in a little vial of plastic vial with iodine methanol, just drop the wafer in, set the whole thing on top, and you go from here to here. So it's pretty spectacular. Other materials have other passivation means, but won't go into that. Okay, now we get into, do any of these measurements agree? TRPL versus RCPCD, which is, I'm calling this resonant coupled photoconductive decay because of the coupling to this resonance. So this is a gallium arsenide, oops, sorry. I'll get this right, but this is a gallium arsenide thin film grown at NREL, 2 microns, probably Dan Friedman's group, that was passivated with gallium indium phosphide that's lattice matched and is an excellent ternary passivation agent for gallium arsenide. So we measured this by TRPL, and we measured it by RCPCD, the same sample. These are the photon fluxes. I had the photons for the TRPL, not for the RCPCD, but they're larger here. And you see roughly, it's around 300 nanoseconds. Now at very low injection level, here we're only putting in 10 to the 16th photons per square centimeter. And something else can happen. If you have some residual shallow traps, at very low injection, they will capture in parallel with the deep traps that determine the lifetime, and you'll see a suppression of the initial lifetime. So you see it's actually shorter here than it is at higher injection. We go to 10 to the 11th and 10 to the 12th, and it kind of levels out around 300. In the photoconductive decay, we have about the same numbers, 300 and some nanoseconds. Then we go to much higher injection and we get into other issues, and these are related to mobility problems that I'll talk about later. So we get some distortion at higher injection level that show up in photoconductivity. If we went to high enough injection level here, we would see a bimolecular decay, and we see a steepening at t equals 0. So there are all kinds of regimes here that will cause problems. But they basically agree 300 nanoseconds is the lifetime that both both measurements show. Now, here's one of the problems with shallow traps. This is the polycrystalline telluride that's used in solar cells. This was grown at NREL by what's called the CSS technique. And the standard way to measure carrier lifetime is TRPL, and typically we will get 2 nanoseconds or so in the best films. That's the best we see. And if you remember SIGS, we got 100 nanoseconds, which is, I think, why SIGS is surpassing gallium arsenide by quite a ways in terms of efficiency. But this is what we see in TRPL. Now, there's a little residual signal here, but you can barely see it. In PCD, on the other hand, we don't have the time resolution to see the primary response, but we see this long decay here. This is the trap mitigated decay. This is the electrons in shallow traps at green boundaries that are being thermally emitted, and so they're emitting electrons for a long time after the primary pulse. And this has nothing to do with the recombination event. It's just a shallow trap event, and it's an artifact. So separating artifacts from real recombination is one of the challenges that we're always dealing with. Show the versatility of the RCPCD. The late Ann Dillon was making single wall nanotubes in a Nafion binder, and just for the heck of it, we ran it in the RCPCD. And actually we have very long lifetimes, and I'm not going to attempt to explain these at all. Let's see, the lifetime being in microseconds, so some kind of a charge separation. I don't know, the complexity in carbon nanotubes is beyond me, but anyway, we were able to measure a long lifetime over a wide wavelength range. Maybe carbon nanotube people can explain that. Unfortunately, Ann has passed away, so.
Then it goes the other way, because the band structure are symmetric. So electron hole doesn't separate. Like silicon, it separates very nicely.
Yeah. So
it should have gone the other way. It's interesting.
Yeah, it is. So we never were able to follow up on that. We lost Dan a couple of years ago, quite prematurely and quite young. But anyway, we were we just had the carbon nanotubes on the platform and saw finite signals. Okay, surface recombination is another big issue. I showed you the silicon wafer that was immersed in iodide methanol, and we had the lifetime change by a couple orders of magnitude. So here's some calculations using a Fourier series model for the transient carrier concentration in a silicon wafer model calculation, all analytical, and we assumed a standard thickness, and we assumed some values of surface recombination. Let me see here, what did I put in? Oh, okay, here, we assumed an S of 500 centimeters per second on a bulk life of a lifetime of 200 microseconds. But what we did change here was the wavelength. Now we can do this with a tunable laser system. And here's what happens. If we put in a strongly absorbed, like this was 750 nanometer light, and the absorption's in a few microns. The carriers are generated near the surface in a Beer's law profile. They recombine very quickly, and so we see a very sharp initial dip, and then a leveling off as the carrier profile flattens in the bulk of the material. We can start with that by putting in very weakly absorbed light, which puts in a flat profile, and we see this kind of decay. So by changing the wavelength, we can see the surface recombination effect very markedly. In fact, I like using a YAG and double YAG, 532 and 1064, that go from down here to up here, to see if surface recombination is a factor. Now, we fit the Fourier series analysis, the same one that I think Van Roosbroek or maybe, well, anyways, one of the pioneers developed that's in the literature, and we fit the Fourier series to the decay curve at 900 nanometers, and now that we get a S of 8642, or about 8,600 centimeters per second. So we can fit that. But if S were 0, this would be a straight exponential, and as S gets, as the wavelength gets shorter, this becomes steeper. So just kind of a ballpark order of, is this a passivated material or not? This works quite well to change the wavelength. Now this has been instituted by Darius at NREL, because we have a problem in a direct band gap material like cad telluride. We're working on cad telluride there, and he has some bulk cad telluride. And because you have the steep band-to-band transition, it's very hard to find a regime where you can get volume absorbed light. So he used the 2-photon absorption. He used a 2-photon absorption here, so he sighted out in the infrared, and the 2-photon absorption, which varies as the square of the electric field in the EM field. Oh, I'm sorry, in the EM field, is quite weakly absorbed. So the 2-photon absorption for this wafer showed 66 nanoseconds, whereas the single photon in the green or whatever, showed about a nanosecond or so. So this indicates the surface is dominant here. It's very comparable to what I did on the silicon, with the 2 wavelengths. So this has become kind of a standard analysis now for the cad telluride and for direct bandgap materials, is to use the 2-photon absorption as a means to get this weak volume absorption and get the absorption away from the surface. Now the surface still has an effect in the asymptotic lifetime if you go back to all the classic papers. I think it's the paper by, let me think, Van Opdorp, I think, works out the analysis for this. So basically the asymptotic lifetime is related to the diffusion time to the surface, and the thickness of the wafer and some things like that. So if the surface is still playing a role here, but you have a flat decay time when you have a flat profile. Okay, microwave reflection. This is commercially available. Basically, it's Maxwell's equations applied to a wafer. Here's the sample. We work between 7 and 20 gigahertz with a directional coupler, have a waveguide here with a sample sitting on the end. My system uses a transparent conducting oxide on this end of the cavity to terminate the cavity, and the light comes through that. The microwaves are reflected off the surface of the wafer, and it's strictly Maxwell's equations applied to this problem, where the incoming wave is typically 10 gigahertz. So the incoming EM wave comes in. Maxwell's equation says that the reflectivity is a function of the conductivity. And so you see this incremental conductivity change produced by a light pulse, manifesting at a transient with a light pulse that persists for the lifetime of the carrier. So again, after you rectify the reflected microwave, you get a transient here. This has been commercialized by a company called Semilab that operates out of Europe, and they make a mapper where the sample was rastered, and I think they use a gallium arsenide laser, and they just raster the wafer and measure the microwave reflection, and then they pick off the exponential, and then they use some algorithm to pick off 2 points and get a slope. And so, okay, this is just Maxwell's equations applied to this problem with a metal reflector at the back surface. The metal reflector gives you a transmission component on the see on the high resistivity side. So without the metal reflector, I think all these flatten out here. And if we work on this side right here, if we're looking at the conductivity or the reflection at 20 gigahertz and put a pulse of light on, then we're moving up and down this curve. And as a consequence, this is just some stuff we made with our homemade single point system. We get these nice lifetime maps. And we have a semi-lab system at NREL that does this mapping. And this is a silicon polycrystalline ingot. I think these are 4, well, pardon me? Oh, let's see, what's the size here? Is that 5, I think it's 500 millimeters by 500 millimeters. It'd be 50 centimeters. No, it's more like, these are more like 4-inch wafers. And anyway, it's color-coded in terms of lifetimes that vary from 0.2 to 2 microseconds. Now, these are the ingots that are grown in a furnace. They have a big die, a ceramic die of some kind. They drop molten silicon in there. It crystallizes into a polycrystalline ingot brick, really. And then they slice these bricks into about 300 micron sections, and they're square. And you see the contamination on this edge of the brick. And this is low lifetime, you have high lifetime areas here. But this is probably the favorite tool of the polycrystalline solar cell people, which is probably the dominant technology out there in the flat band or flat plate residential market right now. Anyway, it shows you where all the defects are and if you have defective areas in the range of lifetimes. So, but they're pricey, they're $300K or so. Okay. This is the apparatus that Don Dunleavy and I recently patented through School of Mines, and we call it Transmission Modulated PCD. Basically, it's RF again. You have a oscillator here terminating in an antenna, coil antenna. You have 2 metallic containers. One has a transmitting coil, one has a receiving coil. You bridge these with a sample, and the RF goes from the transmitting coil into the receiving coil, which is quite simple. It's amplified, turned into DC, and it turns into a transient. The principal operation is you have a long RF path length here from the transmitter to the receiver. And these are data that I did with both the same sample with what we call transmission modulated PCD. And basically what happens is as you increase the conductivity of the sample, the transmission decreases, the RF transmission decreases. Again, classic Maxwells equation. So as the conductivity increases, the transmission of RF decreases, and so you get a attenuation of the RF coming from the transmitter to the receiver, and so you get this kind of transient. I measured the same sample with both techniques and get about the same answer. Now the advantage of what we call the TMPCD is it's very fast. It's not based on high Q, so we get response times of a nanosecond or so. It's detector limited right now. And we were limited here by having a 5 nanosecond YAG oscillator, but this has been moved to NREL, and we're putting it in the femtosecond tunable source out there and incorporating it into a new experiment out there, which I'll tell you about. And the idea is that I think we could resolve a lot shorter times with this than we can with the RCPCD. Why don't we use the microwave reflection? Because both of these techniques are much more sensitive than microwave reflection. I've run the same sample in all 3 pieces of apparatus, and both of our inventions, so if I could use that word, are more sensitive than the microwave reflection, because the microwave reflection is a fairly small technique, and it's kind of hard to see a signal sometimes. So the advantage of this is we have much higher sensitivity to microwave reflection. But what we'd also like to do is be able to measure thin films. And with the RCPCD, the response time is really not appropriate to most thin films. It's much too slow. So anyway, before I leave that, so what we're actually doing, the new experiment in NWEL, is we're incorporating the time resolved PL and the TMPCD into the same apparatus. And the idea is that the light pulse that produces the photoconductive transient will also produce a photoluminescence transient, and we're going to use a fiber optic collector to collect the photoluminescence transient, and then we'll look at both of these simultaneously with the same light source and hence the same injection level. One of the issues with moving between different pieces of apparatus is it's hard to keep the injection level constant, and so you wonder whether the injection level was quite different going from one experiment to the other. So here we'll measure both simultaneously, and out of that we hope to be able to extract things like trapping effects and so forth, because they have quite different responses with the two experiments. It's hard to see trapping in TRPL. The limitation of TRPL is that the photon count has to exceed the dark count of your detector. And if you get into long decay times, the dark count of the detector starts to dominate the photon count. In other words, the photons are being dragged out over microseconds. The photon rate is low, the dark rate may become higher, and so you're blind to the trap emission. We can't really see, for example, cadmium telluride that well with TRPL. We can't see the traps, but we can with PCD. The difference with PCD is the minority carrier is in a shallow trap, but the companion majority carrier is still running around out there giving a signal. So as long as we see the majority carriers via this trapping phenomena. But anyway, we hope to see both with this new apparatus. Now, this is came out of one of my students' PhD thesis, and this is what we call the free carrier pump probe technique. And what he did was he built an RCPCD apparatus, and he combined that with a cadmium telluride detector. So here's the RCPCD apparatus. Let's see now, the sample, okay, so he puts the sample in front of the cadmium telluride, or he flips the mirror in and puts the sample on the RCPCD coil. And he was able to have the same incident intensity both ways. In other words, the pulse is coming in, and it either goes to the sample which is mounted here, or the sample, he moves the sample down here, flips the mirror, and looks at the same pulse down here. Now, in the free carrier absorption, this is really the Drude. You calculate the free carrier absorption using the Drude approximation. This is really just the motion of the free carriers that are being scattered that vary, the absorption which varies as the square of the probe frequency, lambda squared. So we use the CO2 laser, and it's proportional to the excess carrier density and inversely proportional mobility. So this is what you see in the infrared. If you have, for example, heavily doped silicon or anything with free carriers, you'll see this 1 over lambda squared absorption. This is well outlined in Pankoff's book, for example. And it turns out this varies inversely with mobility. On the other hand, the PCD varies as the excess carrier times the mobility. So if we do these two measurements in parallel and take the product, delta alpha times delta sigma, and take the square root of that, we should get something proportional to delta n, which cancels out the mobility effect. Well, we had seen funny things in silicon for a number of years, especially in high resistivity silicon, and we'd seen this kind of turnover at high injection, and we thought it was a function of nonlinearity of our apparatus. So here's the PCD signal. It's coming, it actually is increasing. Here's a nanosecond pulse. We've seen an increase in the conductivity, then some decrease. But actually this is real, and if we look at the free carrier absorption at the same time, we see that it spikes at high injection and then comes back down. So if we take the product of this curve times this curve, we get this curve over here, which is a nice exponential. And so the conclusion that we come out of this is that the mobility has really dropped off, has really decreased at these high injection levels. And we have a fairly simple model of that based on just a solution of the continuity equations with the inclusion of Poisson's equation, and it's called space charge limited current. In the early days of semiconductors, before doping became popular, people would see these effects a lot because they couldn't dope the semiconductors, so you'd have undoped semiconductors. And basically it's this idea: you have electron hole pairs, and then when the density is such that the internal field exceeds the external driving field, then it becomes a plasma. It doesn't want to move in the external field, so it becomes this big kind of semi-neutral plasma. And so the effective mobility, or the ambipolar mobility, decreases markedly. So we had both measurements that measured, for example, the photoconductivity. If we take the photoconductivity and divide it by the delta N we calculate from the product, we see the mobility decreases from, and we include the injection level, which we can calculate from the incident light. We see the mobility increases from 1300 down to about 200. 200 being the initial part of the experiment, this being the tail end of the experiment when the excess carriers have died away. Well, if we go back to basic transport theory and we look at the old textbooks, you know, like Smith and so forth, we see something called the ambipolar diffusion equation and the ambipolar mobility. And the ambipolar mobility has this n minus p term, which says that if n equals p, then the mobility goes to 0. So at low injection, of course, when one is much greater than the other, you go to the minority carrier minority carrier mobility. But at high injection, it says mobility will go to 0. Well, we found a huge drop in mobility, and so we think it's the ambipolar diffusion effect, and we're hoping maybe some of the simulation tools here can do better than our simple model here, which is all analytical in nature, but had a lot of approximations in it. So the consequence of this is that at high injection levels, these mobility effects may be important in things like solar cells. My student, Ari Feldman, just published a paper to that effect in JAP, and I would think this would be of concern to concentrator people if this holds up. But again, it would be nice to have a simulation backup for this to see if the same kind of numbers result from simulation as from our simple analytical model. Okay, anyway, I already told you about this. We're combining TMPCD and TRPL to measure PL and PC decay simultaneously, with the expectation that we'll get information on trapping, among other things, by looking at the differences between these two signals, since one is quite sensitive to traps and the other isn't. And nobody's done this before, so we hope separate recombination from trapping directly that way. But that's a partnership between my company and NREL. But the lab is at NREL where we're doing this. So what are the pluses and minuses? Let's see how we're doing here. TRPL works best for direct bandgap materials. It can resolve very short lifetimes. Randy Ellingson, who's now at Toledo, came up with a variation of TRPL using a what was it called? Time of flight. Anyway, you utilize the space between the sample and the detector as a time metric. And we got down to 100 femtoseconds with that, and we measured the lifetime in 10 to the 20th doped gallium arsenide, I think, for some of the IC people. So we can see short lifetimes. It does not work well for long lifetimes. And it's not that sensitive to shallow traps. That is, if there is a long trap emission signal, it's kind of hard to see it with the TRPL because of the low count rate. On the other hand, the shallow traps can affect the decay at low injection until you fill them, which I showed you in that one of those first pictures. You have to fill the shallow traps, and the trap level is very low in that picture. We had to get down to 10⁶ or so before we could see those. But anyway, by and large, it's probably the best technique out there because it doesn't have the mobility problem built into it, whereas the PCD does. Now, PCD is very, very sensitive to also weak signals. And you see minority carriers in shallow traps via the extended conductivity, very sensitive to shallow traps. You have the downside of the mobility variation with delta N. Now in the Sinton apparatus, he has an algorithm that you put in all the parameters of material, doping and so forth, and he has a little solar cell actually that calculates the input flux for each measurement. So he calculates the carrier concentration as a function of time with his time delay and then puts the mobility correction in there. On the other hand, the Sinton people admit that the technique does not work for high resistivity samples. You get the wrong answer consistently. And so they just say, don't use this. They have another mode called the transient mode where you just shut off the light and watch the transient just like we do. And I wonder if that might be the bipolar effect. I don't know. But this has been an ongoing problem for a number of years. And the mobility variation complicates everything on any PCD measurement. So kind of summary, TRPL is my favorite. It's the easiest to use. It just doesn't work for things like silicon. Mu PCD is nice. It's commercially available. You can map with it. This is still in the lab. We can see things we can't see elsewhere with other techniques with RC-PCD. This is kind of new. We don't know how good it is, but we're hopeful. And this is more of a laboratory curiosity that enable us to untangle these mobility effects. Actually, we're using it for CAD telluride over there. Steve Johnson at NRO is using this to look at some CAD telluride now, getting some results on that. But I don't see it as becoming a widely used technique. And then QSSPC, single crystal silicon only. One of the problems with polycrystalline silicon is what do you use for mobility? We talked about that in our meeting this morning. If you put in one of these polycrystalline bricks, we know what the mobility is for that doping level in single crystal, but what do you use in the model when it's controlled by mobility is controlled by grain boundary scattering. So really, this is really for single crystal silicon only, even though people use it for everything. So people ask, is there a magic bullet? No. And then if you get into complicated devices, what do I do with this super lattice? I have working on a problem like that now. It's even more complicated. So you have the addition of the device structures complicating all of these effects that I'm talking about for just simple materials. So anyway, that's about it, and be happy to take any questions if.
Thank you.
Sure.
Questions?
So, based on the results you got, I think different methods generally give you different shapes of curves. So, how can you extract the lifetime from different shapes of curves? Because sometimes it's like a straight line, sometimes it's like an exponential decay. So, do you have a universal definition?
No. Yeah, I think that was the point of this, that you get all these different shapes.
Yes.
And the shapes can originate from different internal sources. I neglected one of the biggest shape changers that we see, and this is in silicon where you have deep level defects, and you can fill those at higher injection, and then you get a convex decay curve rather than a concave decay curve. And we see this a lot. I mean, what happens is at high injection with the deep level defect, you'll start out with a high lifetime, it'll drift over to a low lifetime. So these shapes really contain all the information, and the answer, what is the lifetime? I don't know. It depends on injection level. In reality, if one were taking the whole, looking at all the data, we would do a lifetime versus injection level, assuming the surface and everything else was accounted for. But it is a function of injection level. And we routinely do plotting in MATLAB with that kind of thing, lifetime versus injection level, where we take the shape, the instantaneous slope, and get a lifetime, and if we can calibrate the time axis in terms of injection level, then we plot lifetime versus injection level. So there's no one answer. It's a function of injection level. And it's the same thing in direct bandgap materials, where at high injection you have bimolecular decay, which varies as delta n squared, 1 over delta n squared, which then levels off to 1 over delta n at low injection. So there's no, when you have that kind of curve, you know a number of things are going on. And hopefully by looking at them, you can deconvolve what's going on inside.
So it's only meaningful, for example, you change the injection level and compare the different curves using a single method.
Right.
And it's difficult to compare like, across different methods.
Well, the three things, you can vary the injection level, you can vary the wavelength, and you can vary the temperature. And all three give clues as to what's going on. Now, we had discussed this morning about traps. At one point, we had a PCD system that was in a cryostat, and that was ideal for looking at traps, because if you see these long tails, like we've seen recently, these long decay tails, and if the decay time increases as you lower the temperature, then you know this is an Arrhenius behavior. So there's a delta E over KT effect there, which is a trapping effect. So you can be fairly certain that you're looking at traps. If it's direct radiative recombination, the lifetime actually decreases as you lower the temperature, because the B coefficient, the radiative coefficient, becomes stronger. So the lifetime will shorten as you cool. So these are all parameters that one can address if the situation requires working that hard. So it's basically, no, there's no magic bullet. You do a number of experiments, and out of those you hope to get enough information to figure out what's going on inside this material. But it's not always easy. Yeah.
Okay, so I take it that it's very common that, like, if you try to like construct just a single model with like kind of like very like stylized parameters like mobility and so on, that you can end up with like kind of conflicts between those rates. So then you have to use like kind of like your knowledge of these techniques to kind of like prioritize, like which ones do you give more weight? Is that like part of your argument here?
Yeah.
And then I guess another question, if you don't mind, is somewhat different, but like if you're trying to look specifically at like thin films that have relatively weak like external radiative efficiencies, like do you think that like TMPCD is a good technique, or do you think that others would be preferable?
Well, my approach is always do everything you can.
Right.
Measure it every way possible there's measurement that's possible. And out of that, hopefully you get enough information you can make some sense out of it. You don't always make sense out of it. Sometimes you have samples that just don't make sense. But yeah, just the more data you can have, the better. Total radiative efficiency is another useful thing. The QE, what you're doing. Sure. This is another indicator that will complement the other data. You know, if you have data that indicates, say, the long lifetime, but the QE is not good, well, then you know that the long lifetime is probably not the right model. So it's the combination of everything you can do that is the best solution to that. And I mean, something like wafer silicon is pretty easy. it's a piece of cake. And if we passivate the surface and so forth, it's pretty simple. Thin film silicon turns out to be really difficult because when as you go closer to thin film, the surfaces become dominant. So I've worked on several thin film projects, and extracting a lifetime from that is really hard because the surfaces were so dominant that I don't really know what was inside. You know, it was completely surface dominated. You're kind of sunk.
But then you mentioned like these like nonlinear bulk techniques, but can you precisely focus on the bulk in a thin film sample, like with your current setup, or is that possible?
They're working on that right now.
Okay.
They're working on some apparatus to try to utilize the two-photon effect to do some depth profiling. So it's not trivial, but it's a optics problem, really.
Mm-hmm. Makes sense.
As to what area you're actually looking at.
Right. No, I can imagine there's a fraction of and so on.
Right, yeah. So, yes.
Have you noticed, and obviously you measured lots of different samples using lots of different techniques, and you mentioned that there's such thing as too low injection and such thing as too high injection.
Right.
Maybe somewhere in between. Have you noticed sort of a rule of thumb for where that window is on either side of the measured carrier density?
What I would do ordinarily, usually I have some kind of variable attenuator and just start looking at the pulse, going as low as possible, thinking the lowest injection that I can measure is probably more indicative of the quality of the sample and the real low, the impurity content. But then crank up the intensity gradually and look at things change. For example, if there is a shallow trap contribution, I will see the shallow traps fill up, and then the lifetime will stabilize and stay the same over some level of injection. And then as you go into higher and higher injection, you'll see the deep levels come into play, and so you go from one shape to another. So again, just kind of trial and error has been my approach to this. See what happens as you change the parameters and see if they make sense to you. Yes?
So if my understanding is correct, that in a typical TRPL measurement, initially you inject with very high intensity light into your sample.
Well, I would start with the lowest intensity that was possible.
Right. So,
yeah.
So my point is, initially you would have very high absorption near the surface.
Right.
So you see an initial rapid decay of your TRPL.
Well, that is true if the surface is not passivated. Now, most of the gallium arsenide I look at anymore has gallium indium phosphide, so it's very low surface recombination velocity. If I looked at a bare film like we did 20 years ago before gallium indium phosphide came along, yeah, in fact, that was the subject of some contention way back when I was first at NREL, where certain researchers said they had good gallium arsenide solar cells, and we measured it, and we didn't know any better. No, they're not. It was really the surface effect.
Right.
So
initially, you have this rapid decay to the surface. And
right.
You say as time progresses, your minority carrier concentration begins to decrease. Most of them begin to recombine and disappear, and then you begin to worry about the trapping effect, shallow traps.
Right.
So,
right.
Then I'm wondering, in this case, does it make sense to do a two-photon generation technique? But you inject lots of photons into your sample. So at the same time, while you're avoiding the front surface recombination effect, you also sort of saturate the traps. So your decay will be just your bulk effect, without the trap effect.
That's a good question. We're too new at this at CAD telluride because we've done some in CAD telluride, and we see slight improvements over the one photon lifetime, but nothing dramatic like I showed in this crystal, which was a single crystal. My guess is that we probably would not see the shallow traps from grain boundaries with the two photon, because the count rate is too low, and it's just hard to see. It's hard enough to see them with one photon, much less two. So I think we wouldn't see traps there. So maybe answer to your question is yes, this would be a trap avoidance strategy. Yeah. But I always go that the lowest injection is probably the most applicable and meaningful, except in these cases where there are some insignificant things like shallow traps that maybe you have to fill before you get to the real low injection lifetime. But it's kind of, it's not automatic. You turn it on and you play with all the stuff and you look at it, watch it change, and then work till it makes some sense to you.
Any other questions?
So in the case of TRPL, one has an option to look at the decay at different wavelengths if there is emission at different wavelengths.
Right.
But is there a similar possibility in PCD experiment?
Oh yeah. I had over at NRO, I have a tunable system, and we scan the whole wavelength range. And in fact, that's what I did in that one experiment I showed. We have a tunable OPO, and we start out and scan from the infrared into the green and watch the character of the decay change. And when you get these dramatic changes, you know that you have an unpassivated surface, for example, as you go toward the green. So yeah, I used to just put on a sample and turn it on, all scan, and look on the digitizer and watch it scan through the whole wavelength. Then I'd take data afterwards, just kind of see what was there. And then I could change the intensity and do it again. So change all these parameters, yeah.
Okay, last question.
Yeah, one more question is for a silicon wafer, you use a different wavelengths to detect the different lifetime. So how can I explain that the different wavelengths will give you a different lifetime concept?
Okay, what happens is when you use shorter wavelengths, they're absorbed near the surface. You have Beer's law profile. Maybe 500 nanometers. The Beer's law absorption length is a micron or something like that. I'm just guessing. So you're putting all the carriers right at the surface. And so initially they see a lot of surface and not a lot of bulk. So the surface sucks them up like crazy, so the lifetime really shortens. Then the ones that live through that diffuse away from the surface because of the concentration profile. So they diffuse away, and at enough time, you have kind of a flat profile. In fact, with finite acid surfaces, you have kind of a barrel-shaped profile like this. I had a nice QuickTime movie that showed this evolving in time from t equals 0 and up to t equals infinity. So you go from Beer's law to kind of a flat profile, in which case the surface is killing carriers, but majority of them are being killed in the bulk by deep defects, because the bulk dominates the excited area. So that's why you get this dramatic change.
Okay, so thanks for sharing all of your experience and wisdom.
You're welcome. Thank you.